Hey guys, so we're going to start chapter 8, the binomial and geometric distributions. This is one of my favorite chapters. It's the last chapter we're going to do in probability. So, giving you a pop quiz on quantum electrodynamics. Presumably a topic you know nothing about, and if you are a QED expert, just pretend you're not. There are 4 questions on this quiz, and there are 4 multiple choice options for each of these questions. What is the probability that you'll get exactly 1 question right, no question right, or 3 questions right? Now, if it's a multiple choice question, I have a question and then I have answer choices A, B, C, and D. What is the probability that I get one of them correct? Well, there's 4 answer choices, so 1 out of 4, or 0.25 is the probability that I get one of them correct. But now I'm going to ask, what about no questions right or 3 questions right? So I could get 4 questions correct, 3 questions correct, 2 questions correct, 1 question correct, or I could get them all wrong. If I got them all right, that means I'm going to use R to indicate that I got it correct, right? And W to indicate that I got it wrong. So if I got it right, if I got 4 of them right, then that means I got question 1 number right, number 2 right, number 3 right, number 4 right. And the probability of getting a question correct was what? What did we find on the last slide? That was 0.25, 25% chance. So I'm going to do, and because each question doesn't affect each other, they're independent. Remember that with independent probabilities, we're going to multiply them. So I'm going to do 0.25 for this right answer times 0.25 times 0.25 times 0.25 for the 4 questions. So I'm going to raise that to the 4th power. That's the same thing as saying 0.25 times 0.25 times 0.25 times 0.25, right? All right, that one's easy. When I put that into my calculator, I get 0.0039. So that's a very small percent chance that I get all 4 of them right. For 3 questions right, I could get number 1 right, number 2 right, number 3 right, and then the 4th one wrong. I could get right, right, wrong, right. Or I could get right, wrong, right, right. And the last one, I could get the first one wrong and then the next 3 correct. Now remember, this is a test, so each question is independent of each other. I have to count all 4 different ways I could get 3 right and 1 wrong. So there's 4 different ways, so I remember I have to multiply the probability of this 4 times for each one, times the probability of getting it wrong, which is 0.75. I'm doing it for this last one. Times the probability of getting them 3 right, so 0.25 times 0.25 times 0.25, or to the 3rd power. And let's see how much. What do I get for that? I get 0.046, and I'm going to round that up to 9. For 2 questions correct, I could get the first 2 right, the next 2 wrong, or I could get wrong, right, and I'm doing this completely out of any specific order, so wrong, right, hopefully I get them all, right, wrong, right, wrong, wrong, right, wrong, and then I think the last one is right, wrong, right. Yeah, there we go. So I have 1, 2, 3, 4, 5, 6 different combinations. Now, if the question were there's 10 questions, and what are all the possible answers I could get for 10 questions, this is too long of a process. So I'm going to start talking about binomial distribution and how we can find a shorter way to do this instead of doing this whole long process of finding all these probabilities. The situation we just explored fits the conditions of a binomial setting. Each observation can be labeled either success or failure. So there's no more or no less options than success or fail. On the last problem, we either get it right or wrong. There's no in between. You flip a coin, heads or tails. You either get heads or you don't get heads. Are you wearing red or you're not wearing red? Are you wearing sandals or you're not wearing sandals? There's only two options. You either succeed or fail. There has to be only two options whenever you do these problems. Is there a fixed number of observations? Do you have a set number of observations you're looking for? In the last problem, there was 4 questions. Did I get 4 of them right? Did I get 3 of them right? Did I get 2 of them right? There was a set number of observations that we had. The different observations need to be independent of each other. So, for independence, make sure that sometimes they won't say it's independent, and you have to think back to what we've already learned of independence. Are dice independent? Yes, dice are independent of each other. When I flip a coin, is that independent of each other? Yes, it is. When I do cards, when I'm pulling cards out of a deck, is it independent? Only sometimes. When is it independent? Is when I put it back, when I replace the cards. If I don't replace the cards, then the card that's changing the probabilities, and they are dependent of each other. So make sure you're aware of when stuff is independent and when it's not. And the last one, the probability of success needs to be the same for each observation. So if on that electrodynamics pop quiz I gave you had the first 2 questions as A through D answer options, and then the last 2 questions as true or false, my probabilities change so that it doesn't have the same probability for success on each question, so it's then not binomial. So make sure that we meet all 4 of these conditions before we say something is binomial. In general, if data are produced in a binomial setting, we say X is the number of success in a binomial random variable, and the probability distribution X is called a binomial distribution. We've already talked about a distribution called the normal curve, right? The beautiful normal curve that we always talk about. Well, now I'm going to introduce a binomial distribution. The binomial distribution has 2 parameters. I'm going to write n so we all know that this is the normal curve, right? And for a binomial distribution, instead of having the mean and the standard deviation, we have the number of observations, n, and p, the probability of success for any given observation. The possible values of x need to be whole numbers between 0 and n. The abbreviation for when we abbreviate binomials, we're going to use b parenthesis n, the number of observations we have, comma, with the probability. Think back to when we were doing the normal notation. N represented that it was normal. Mu, we have represents our mean, and then sigma represents our standard deviation. It is extremely important that you can recognize when a random variable is or isn't binomial. There's 4 conditions. We already talked about them in the last slide. So make sure you recognize if something is binomial or not. So we know that blood type is determined by a person's genetic makeup. If both parents carry genes for both O and A blood types, a child has a probability of 0.25 of getting both O genes and expressing the type O blood. Different children of the same parent inherit genes independently of each other. Think of your brothers and sisters if you have any. Do they have the same blood type as you? Not necessarily. Just because you have the same parents doesn't mean you have the same blood type. So call X the number of siblings in a family with 5 children who express type O blood. Does this satisfy our conditions for a binomial? Well, what was the first condition? Success or fail. What's succeeding? Well, succeeding is having type O blood. Does it meet that requirement? Yes. It's either you have type O blood or you don't have type O blood. Second one. Do I have a fixed number of observations? Fixed number of observations? Yes. I'm looking for 5 children. Let me write that out. Children that have type O blood. Next one. Are they independent? Yes. They told us it was independent right here. Where is it? Independently of each other. So check They are independent. And the last one is the probability the same, and I gave away the answer, is the probability the same for each child? Yes, a child has a probability of 0.25 for getting type O blood. So yes, it satisfies our condition, so I'm going to go ahead and write B, it's binomial, the number of observations is 5, and the probability is 0.25. Remember, you write B, N, comma, P. We can apply this knowledge to sample statistics. Say we choose an SRS of size N from a population with proportion of P successes. When the population is much larger than the sample, the count X of our successes in a sample has an approximately binomial distribution with the parameters N and P, given that they meet the 4 conditions. So we can use this whenever we have a population that is much larger than our sample and do the binomial distributions. That's only if it meets the 4 requirements, the 4 conditions that we talked about. The binomial formula. When we calculate the probability of getting 0, 1, 2, 3, 4 questions right on the quantum electrodynamics pop quiz that I gave you at the beginning of class, or we pretended like we took, we had to multiply by the number of possible ways we could have achieved each number of successes. If I got one question right, there was many different possibilities. I could have gotten right, wrong, 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 right, wrong, 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 right, wrong, and then the last one I could have gotten wrong, 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 right. Thinking back to that first example. Well, when we have N that gets much larger, this gets extremely complicated. Imagine if we had 10 questions and we had to do all the different ways, the number, different possible ways that we did 10 questions. I'm going to use this binomial coefficient to give us the number of ways we can arrange K successes among N observations. So, whenever you see N, K in parentheses, it means N, the number of observations, choose a certain amount of them to be in a certain order. So, for this question, there's 4 questions, and I want you to choose one when there's 1 correct. And then it'll give you this formula over here. But I'm not going to have you guys calculate this. Well, what factorial is, if you've never seen factorial, you were supposed to learn that in middle school, is 4 times 3 times 2 times 1. It's like a recursive formula for sequences in series in Algebra 2. And then over 1 factorial times 4 minus 1 factorial. And I'm not going to have you guys worry about this because the calculator does everything for us. So I just want you to realize that N choose K is not the same thing. This does not mean N over K. We're not dividing. This is not a fraction. It's N choose K is called the binomial coefficient. And we need this in order to do binomial distributions for our formula, which you're going to see in the next slide. The binomial formula, given our new expression for the binomial coefficient, we can now give you a formula for a binomial probability. If X has the binomial distribution with N observations and the probability of P successes on each observation, the possible values of X are 0 until N. Whatever N is our number of observations. If K is any one of these values. So, let's think back to the first example. When X equals, let's say, 2, if I want 2 correct on my pop quiz, I'm just going to plug everything in to this formula. This is on the reference sheet. Don't worry about this. Do not freak out about this formula. All I'm doing is plugging in numbers for N, P, and K, and we can all find out what N, P, and K is. So I'm asking what K is right here for 2 correct. X equals 2, which equals, how many questions were there on that first example? There was 4. Telling you to choose 2. Give me all the different arrangements of when 2 are correct. The probability of each question getting it correct was 0.25. K is 2. 1 minus 0.25, the probability, to the 4 minus 2, n minus k. That's simple. You're going to have to write this formula down on your AP exam, on my test, on your quiz. So make sure you locate this formula on the reference sheet and make sure you know how to use it. Just make sure you know what n is, what p is, and k is, and you should be fine. Suppose an engineer chooses an SRS of 10 electronic switches out of a shipment of 10,000 switches. Suppose also that 10% of the switches are bad. This doesn't 100% fit the condition for independence, but we're going to approximate a binomial distribution anyway. What is the probability that an engineer chooses no more than one defective switch? So, no more than one defective switch is saying 0 or 1. So I'm going to have to do the binomial distribution formula for when k equals 0 and also for when k equals 1. So I'm going to look up that formula on my reference sheet, and so the formula says n choose k, probability of k times 1 minus the probability of n minus k. So I'm going to do that twice. I'm going to do that for when k is 0 and when for k is 1. N is the number of switches I have. So n is 10. P is the probability that the switches are bad. So P is 0.1. And K is right here in the question. What is the probability that an engineer chooses no more than one defective switch? So I'm just going to write in my formula. 10 is N. K is, for this first one, when K equals 0. The probability is 0.1 to the K power times 1 minus 0.1 to the N minus K. 10 minus 0. And then I'm going to add that to when k equals 1 and do the formula for now when k is equal to 1. So 10 over 1, 10 choose 1, 0.1 to the first, 1 minus 0.1 to the 10 minus 1 power. And you are going to have to write this down for the AP exam, for my tests, for the quizzes, so make sure you know how to plug this in. And I would go ahead and simplify this. 1 minus 0.1 is 0.9, 10 minus 0 is 10, 10 minus 1 is 9, so make sure you write it in simplified form. Now, I'm going to show you how to do this in the calculator, but this is how we write it again. 10, choose 0. 0.1 to the 0 power, 0.9, 1 minus 0.1 is 0.9 to the 10. And when I use the binomial coefficient, I get 1. And for here, the binomial coefficient, I get 10. Remember, 0.1 to the 0 power is 1, so that's how they got this. And then this is the answer. Now let me show you how to do it in the calculator, and it's so much easier. But before I do that, some important abbreviations. PDF is a probability distribution function. It's not a file on your computer. Well, it is, but not in this example, or not in statistics. Given a discrete random variable x, the PDF assigns a probability to each value of x. These probabilities satisfies our previous rules. So, for example, when I have the probability that I'm looking for x equaling to 5, I use PDF when it's exactly 5. When I have 5 questions, when I'm looking for 6 switches that fail or are bad. When they ask you for exactly an exact amount, it's equal to, and we're going to use PDF. CDF is cumulative. So given a random variable x, the CDF of x calculates the sum of the probabilities starting from 0 up to whatever number you tell it to do. So the probability of at most x successes is, or whenever you see x is less than or equal to a number, that's when we use CDF. Like I said, remember it says it calculates the sum from 0 to a number, just like on the normal curve. The area is shaded always to the left. Your calculator does the same thing. It goes 0 to a number. So if I'm looking for the right side or greater than, we're going to have to do 1 minus, just like we did for the normal curve. So on your calculator, once you've established that x follows a binomial distribution, we're going to use the calculator to find the probabilities. Now, this is a great shortcut if it's binomial. Make sure you see right here where it says vars, we're going to hit second because we want distributions. And then you're going to click down and it's going to say binomial PDF or binomial CDF. If you need help with this, just come in and see me and I'll show you where it is on the calculator, but you should be able to find it. It's under second distribution and you're looking for, scroll down all the way down to binomial PDF or binomial CDF. We use PDF, remember, when it's equal to. We use CDF when it's less than or equal to. And then how I remember to put it in the calculator is N, comma, or napkin, NPK. And then the same thing for CDF. It's still NPK, napkin, number of observations, probabilities, and then the number you're trying to find. So suppose our multiple choice quiz on quantum electrodynamics, which we still know nothing about, has 10 questions. So we're guessing on this 10 question test with 4 answer choices. What is the probability you get exactly 6 questions right? First, I'm going to write it using the formula, and then I'm going to write it how we would plug it into the calculator. So using the formula, it's going to be 10 questions. Remember, n is 10. The probability for 4 answer choices A through D, the probability of getting it correct is 1 out of 4, or 0.25. And then K for this question says exactly 6. So K is 6 for this first question, question A. So I'm going to write 10, choose 6. The probability of getting it correct is 0.25 to the K power times 1 minus the probability, 10 minus 6. And that simplified would be written as 10, choose 6, 0.25 to the 6th, 0.75 to the 4th. And these two exponents should add up to the amount of questions you have. So 6 plus 4 does give me 10. So you did make sure you did that right. Now, in the calculator, go ahead and put binomial. This is a PDF question because it says exactly. I want when x is equal to 6. Binomial PDF. Number of observations is 10, comma, probability, 0.25, comma, I want when there's 6, exactly 6 questions right. And go ahead and put that in your calculator and tell me what you get. And the answer's on the next slide, so we'll get there. What is the probability that you get at least 6 questions right? Now, for this one, at least 6 means 6, 7, 8, 9, 10. There's 10 questions. So what's the probability that I get a 60% or more on this test? Well, remember I told you that the calculator only does from 0 up to a number. And I want from 6 to 10. So what I don't want, remember that the probabilities always sum to 1. So I can do 1 minus whatever I don't want. What do I not want? I don't want 0, 1, 2, 3, 4, and 5. So I'm going to tell my calculator to do binomial CDF, because cumulative from 0 to a number. 10 is my N, my P still is the same. My K now is 5. Notice that I didn't put 6 because I do want 6. So I'm going to have 1 minus my binomial CDF for the probability that I get at least 6 questions right. And here, this is what you should have gotten. When you plug in binomial PDF, you should have gotten 0.0162. And remember that at least 6 questions right means I'm doing the PDF for 6, 7, 8, 9, and up to 10. Or you could just do 1 minus CDF in your calculator, and you would get 0.0197. Here's the homework for tonight. The first few questions are telling if it's binomial or not, and then the next few questions are calculating probabilities using the formula.